So let me introduce Thomas Kipf to you. I'm very happy, and I think Volker and Paolo as well, that Thomas accepted our invitation. So Thomas is one of these people, which makes science enjoyable because they just do their PhD and have great impact by doing the PhD, and then of course all the rest of their research. So Thomas was this person that was showing that many things that previously were done in a non-differentiable way with structured knowledge like graphs can also be done in a differentiable way. And so I think he's most famous for now, but I expect much more for his work on graph convolutional networks. And I guess that's also why he would like to talk about relational structure discovery. So Thomas, really a big thank that you joined. It's amazing. I've read, I guess, almost all of your work. Looking forward what I can learn today. Thanks for joining.
Well, thanks, Christian, and thanks everyone for the invitation, and also for these kind remarks. I'm super excited to be here, and I mean, to me, it came as a surprise to be able to speak here as the first presentation. So that's like a big honor. So yeah, thanks for that. And I want to talk today about relational structure discovery. So this is a topic I'm personally very excited about. Basically, going beyond learning with data that is given to us in the form of relational structure, like a graph, but actually being able to use inductive bias of models for more natural data and discovering the structure that we actually care about. And this is work that stretches through my PhD at the University of Amsterdam, but also now at Google Research in the Brain team here in Amsterdam. So what do I mean by relational structure? So the idea essentially, so what I mean by that is essentially graphs and networks. So the core idea is to represent the world's information in terms of entities and their relationships. So that's like the core concept of a lot of relational learning. But I think very often we just take this structure for granted, and we don't really think about the core aspects of why is this even a useful abstraction, and how isn't it remarkable that we as humans can very easily represent the world in this kind of abstraction. And so this form of abstraction, thinking about the world in terms of entities, objects, concepts, is very easy for us humans to interpret and becomes very natural for us. One might even argue it forms part of the basis of our kind of higher level cognition in terms of language being able to communicate. We need to be able to form these kinds of abstractions just from low level perceptual input that we get for our senses. And this abstraction is also near universally applicable. We can essentially treat almost everything out there as entities and relationships, from the very small things like atoms in the universe and their kind of physical relations and forces between them, but also all the way up to biological systems, societal networks, structures like the internet. We can think about entities in all kinds of fashions. And this relational structure allows us to also perform compositional combinations of these things. So we have infinite ways in which the information in graphs and networks can be recombined, and the important bit here is that it can be sensibly combined. We can think about all kinds of entities and their relations, and we can use the simple kind of blueprint to reason about a lot of different kind of structures and a lot of different kind of information in the world out there. So graph structure data in the wild is also, not surprisingly, in technology, a very important representation. You have social networks, citation networks. You can think of maps and road networks as essentially nodes of intersections, and roads as edges or relations between them. Communication networks, energy networks, the World Wide Web, but also things like knowledge graphs, things like interacting physical systems or dynamical systems, where you have temporal interactions or causally interacting temporal components, or protein interaction networks, where you have biological networks, proteins, molecules, and so forth that you can nicely abstract in the form of a graph. So the field of graph representation learning is essentially something that came about in the past decade or so, and graph neural networks especially have been now a very much established method for learning with graphs. And surprisingly, so these have been only really taking off in the past 5 years or so. even though earlier works have already been around for much longer than that. And graph neural networks are essentially methods that you can allow it to differentiably learn about compositional reasoning tasks if you have the right structure in terms of entities and relations available to you. You can perform node, edge, and graph classification with those methods, and also things like physics modeling. So you can learn differentiable physics simulator, because essentially they have the same structure as a physics simulator, but then as kind of learnable components. And the typical assumption here is that we know what the types of entities and very often also the relations are. Like if you want to do a physical simulation for a graph neural network, you have to provide the coordinates or some kind of form of abstraction of the like atoms or individual components if you want to use graph neural networks for that. And so this brings me to the topic of my talk, which is about essentially what can we do if we have incomplete knowledge about relations. So these are things like link prediction in the easiest case, where you have like partial knowledge about a graph, but you want to complete a graph. Or relational inference in the more general case of neural networks. So you want to infer links or relations, or maybe even causal relations from scratch by just looking at observational data with some further assumptions about it. And then the question is also like, what if you don't even know about the nodes or the entities or the objects that make up the description we want to care about? What if we're just like faced with some kind of raw perceptual data or some natural data? And this brings me to topics like object, entity, or event discovery, and especially from a viewpoint of grouping or clustering of low-level features as one form of abstraction learning. And so the talk will first focus on the relational topic, and I'm going to talk about a few methods in this area, and then I'm going to present two methods in the attention-based grouping or clustering framework for entity discovery, both for attentive grouping of visual features for object discovery, and also attentive segmentation of temporal features for event or episode discovery. And I'm going to conclude by showing how this can all be combined like an end-to-end framework that you can apply on dynamic data. And that's a framework that's sometimes called a structured world model. So the background for all of this is essentially the graph neural network framework. And as you're probably all familiar with, this framework has been around for quite some time. Among other papers, like there's a graph neural network model paper from 2009 that introduced like the overall framework, and there have been many iterations on this idea since then. But modern graph neural networks roughly follow the same structure. And the main idea is to pass messages along the edges of a graph, to agglomerate these messages and to transform the result. And also the messages themselves can be like complicated functions of the neighboring nodes. And by a graph, I mean essentially a tuple of a set of nodes and an associated set of edges. And unless like otherwise noted in the talk, I'm going to represent node features as vectors hi and edge features as vectors hij. And so the most like general framework that most people use these days is a neural message passing formulation of graph neural networks that also forms the basis of graph nets, like the DeepMind paper from a few years ago. And the idea here is to essentially represent both these node update functions and the edge update functions, like the message functions, as learnable functions of their respective neighboring features. So let's say you have edge update functions that take into account like neighboring node features and maybe some feature on the edge that you are given by the data set. So you would iteratively apply an edge update functions across all the edges in the graph, and then node update functions by agglomerating these edge messages, these hij features from all the incoming or outgoing links for a particular node. And these functions, most of the time, are just simple multi-layer perceptrons. And you can also have additional node features in your data set, like xi in this case. And so this framework encapsulates a lot of things, like it encapsulates convolution-based graph neural networks, like that also have been around for some time, and that's been some of my work also on like graph convolutional networks. where essentially the main difference to the message passing framework is that the edge update is a linear function of the neighboring features, and you have some kind of edge weight that you either pre-specify or you learn. Then relational models, they typically assume that you have like discrete relation types in your graph, and then you have particular update functions or update weights for each like edge type. And this is particularly useful for things like knowledge graphs, where you have like typically discrete edge types. And these are still quite scalable models. And then lastly, you have things like multi-head self-attention, which essentially fits in this relational framework. But then the only difference is that the edge weights, the aggregation weights are learnable functions of the neighboring features, typically used by like dot product softmax attention. And so now knowing this kind of framework, it's very easy to think of like ways of doing like learning on graphs with this kind of framework. So one typical recipe for this is to essentially just take some kind of graph data set and do a few rounds of message passing to get updated node representations, and then which we could call a GNN encoder. And then you can read out the final representations and perform like node classification by putting a softmax classifier on the final node representations. Or you can perform graph classification by aggregating node representations by pooling them somehow over the graph. Or you can do graph completion or link prediction, which is what I'm going to explain here, by essentially predicting like classifiers or output decoder functions that take into account two pairwise node features. Like in this case here, you encode representations given some kind of incomplete graph, and then you ask about, okay, are these two nodes now connected, which is something that you might not know because the graph is incomplete, or you mask out some of the edges during training. And that is something you can very effectively train with contrastive learning, like, for example, was done in the graph autoencoder framework or in some more recent works. And there, basically, the contrastive loss would just mean that you have like a positive example and you contrast it against many possible negative examples, of which there are, of course, like quadratically many in a graph data set. So you wouldn't want to like compare against all possible negatives, but you would like to sample a few of them. So this is essentially already the kind of framework that one can use to like learn about incomplete graphs, and it works surprisingly well. And you can even use it to transfer like inductively from one part of the graph, learn this kind of encoder, and then apply it on a different part of the graph at test time, or on new features at test time. But I think the more interesting question is what happens if we actually have no knowledge of the relations whatsoever. Like if you're just given some kind of observation of a physical system, and we would like to learn about like what do the interactions mean, like what are the like forces governing the interactions, like what are the functions governing the actions, and what is the structure underlying these interactions, which it's a setup similar to causal discovery, but slightly more general, because you can ask, okay, what are the types of interactions? Like you can try to cluster interactions into different facets and different types, and not just ask about like binary relations of is there an edge or is there no edge. So, and this framework is also a relatively simple method. So essentially what you can do to learn about relations in this kind of fashion is to frame it essentially as an autoencoder, where now we observe some dynamics, which is like the dynamics here are now given to us in the form of individual trajectories for each node in the graph, which could be like an atom in a physical system or a user in a social network. And then you would encode these temporal dynamics using a graph neural network encoder. And the graph neural network encoder in this case would operate either on the fully connected graph, or if that's too expensive, you could have some kind of local approximation, like a k-nearest neighbor graph in this kind of input space. And the whole purpose of running this graph neural network encoder is so that it learns representations of the relations between nodes, so that then you can ask the model, okay, what is your best hypothesis for how these nodes are actually connected and how they're interacting? And you can read this out by, for example, framing this as a discrete latent variable inference model, and you try to infer essentially the like the types of the edges, or whether there's an edge or whether there's no edge. And you can train this using like discrete variation autoencoders using like this ComplLE softmax trick as like one version of like making this tractable. And then having this like discrete latent graph, we can now run again a graph neural network on this representation, and we can decode or predict the future of the system given this hypothesis of how things should interact. And the idea is if the model gets the interactions correct, it should be very easy for it to model like the physical dynamics. But if it gets like some kind of random graph, then it's going to have a much harder time predicting the dynamics of the interacting system. And all we need to do to train this is to essentially have a reconstruction loss and maybe some kind of regularization loss to make sure that these graphs are actually sparse if you care about sparse graphs. And this simple framework essentially allows us to, on the one hand, accurately model physical dynamics, which is something that was known already. Like you can use graph neural networks to model physical dynamics if you have like an interaction graph given to you. But you can also at the same time discover these latent interaction graphs. And for these kinds of physical systems here, like some particles connected by invisible springs or physical harmonic oscillators coupled by coupling constants. And there's always some kind of latent coupling graph behind them. And essentially what this experiment here shows is that this kind of model can recover them to like a very high accuracy. And at the same time model the future dynamics of the system, for which it needs to know these interactions. And so this framework has since also been extended to things like amortized causal discovery, where you would, like in a framework of nonlinear Granger causality, so like a weaker form of causal discovery that some might not agree even corresponds to like the Attenti causal inference framework. But essentially the idea is to say, okay, if you now treat this model as a binary classification problem, is a node connected to another node or is it not connected? So you just want to infer binary edges, then you essentially, the system reduces to like a causal discovery system. And at the same time, you can also infer other types of structures like now in what I presented before, you don't really have any assumptions about the structure you want to infer. Only you say, okay, it should be maybe sparse. But you can also have other constraints on top of the structure. Like for example, you want it to always be a spanning tree. And this can be done by combining it with an inference technique called stochastic softmax tricks from this paper from Paulus and Joy. And essentially here, this allows you to then use this same technique to infer useful latent spanning trees if this is something that is interesting for a particular task. And this already concludes the first part of my talk about relational discovery. So essentially I talked about like how can we use graph neural networks to complete graphs given incomplete but partially known relations of a graph. But also how can we actually apply these kinds of models for systems so we don't have any knowledge about the relations whatsoever, which is often the case in kind of many physical systems if you want to like learn about physical dynamics or physical laws in systems. But the second part of my talk, which is something I'm personally most excited about, is what can we actually do if we do not even know what good like entity abstractions are? Like what if you're just presented with some kind of naturalistic kind of perceptual input, like a visual input or some kind of temporal trajectory of an agent, and we want to make sense of it. Like we want to make useful abstractions that are useful for a particular task at hand in kind of an end-to-end differentiable way. And this is like the question that has motivated two recent works that I've been involved in. One is called slot attention for attentive grouping of visual features, and one is called ComplLE for attentive segmentation of temporal features. And I'm going to start with slot attention, which is the model here on the left, which was joint work with an intern, Francesco Locatello, last year at Google Research. And here the idea is essentially to have an iterative attention mechanism that learns abstractions from visual input that you can then use to do like symbol-like reasoning on top. And so the idea behind slot attention is essentially to have a single differentiable component that can be placed on top of an encoder, for example, that maps from some kind of visual space or some kind of like lower dimensional feature space into an abstract set representation. And the set representation here is something we call slots. So each slot would represent, for example, a vector that can bind to a particular object in the input. And the way this binding process is done is by a recurrent routing process. So in the very first step, the model would kind of have a rough guess of like what the objects are, and maybe doesn't really break the symmetry correctly, puts two objects in the same slot. But then with like ongoing routing, the model kind of figures out and kind of decomposes the scene correctly into its constituent parts. And this can be both trained in kind of fully unsupervised way by just decoding and reconstructing the input features using an autoencoder architecture. But you can also train this in kind of a partially supervised way, where you just use the slot attention module as an interface between your visual input and maybe some abstract set of labels, like some symbolic description of your individual objects in the scene, like their color, their shape, and so forth. And so the idea here is to have like a set as a target, and the model produces a set. So all you have to do is kind of a matching between the predicted set and the truth set, and you can train this model end to end. And the core prediction problem, as I mentioned here, is basically to learn a mapping from some kind of lower dimensional feature grid or some lower level feature grid to a set of variables that we call slots. And intuitively, each of these set elements or slots should capture an object, a part, or a part of, or like the background of the scene. And this might remind you of capsule networks, because in general, like the high-level pitch idea of capsule networks is quite similar. But one big kind of downside of capsule networks is that they assume that you have one particular capsule for each type of object. So you would have like a house capsule, you would have a tree capsule, you would have a person capsule. But then you run into problems if you have two houses or two persons or two trees in an image, because you would have to essentially for each kind of extra instance already know in advance that you have to have multiple capsules. And if there's multiple things in an image, then often these end up in the same capsule, which doesn't lead to perfect decomposition. And to resolve this, essentially, we have to make an assumption that the representation is essentially universal. So every slot can actually bind to any kind of thing in the input, and that they're symmetric or exchangeable. So they truly form like a set representation, whereas capsules form like an ordered representation, where like the ID of the capsule tells you about the type of object it covers. And so with these slot-based models, we can then learn to decompose scenes into objects. And the idea behind what the model is actually doing is relatively simple. You can essentially view it as a learnable differentiable clustering algorithm. And it's heavily inspired by something like soft k-means. So you could start by initializing the slots, for example, by initializing them from a normal distribution at random, so that they're kind of symmetric under permutation. And then for a number of time steps, you would compute scores as a dot product between transformed input features and transformed like slot representations using some learnable functions k and q. And you would use a softmax attention over these scores, normalized by some temperature. But the core idea here is that the softmax is now normalized over the output axis, like over the slot axis, which is different from things like self-attention transformers, which are always normalized over the input. And because we normalize over the output, we have to now aggregate the input weights, the input features, transformed input value features, using a weighted mean instead of a weighted sum to make sure that the representations don't blow up. And lastly, because we want this module to kind of be learnable and be flexible, parameterizable, we update the slot representations now with a gated recurrent unit using essentially a recurrent update that learns how to make use of the new updates and to update the slots given the new evidence from the input. And if you compare this to soft k-means clustering, this is actually fairly similar. So in soft k-means, essentially the only differences are that the dot product is replaced by a simple Euclidean distance without being in a kind of a high dimensional learnable space, but you would actually do this in the original space of the features. And you would similarly have like a softmax attention kind of over the normalized over the outputs in the weighted mean, but you wouldn't have like the key query and value transformations, and you also wouldn't have a learnable kind of recurrent update function, which is quite important because the model needs to be able to like propagate gradients well. And if you just replace something, that usually works significantly worse in deep learning architectures than if you have like some kind of residual or some kind of gated update function. And on top of that, you have the model has more flexibility in kind of ignoring inputs and in using the new evidence to update the slots. And the softmax attention also has a nice side effect. It means that slots have to compete for explaining the input, because we normalize over the slots. It means if two slots are roughly similar but not the same, that means their attention weights will typically be vastly different because of this normalization. And that means that over time they drift apart and everyone specializes to a particular object in the input. And the overall architecture is then relatively simple. We essentially have a CNN encoder that encodes the scene, like a clever scene here with like some very simplistic objects. Then having the slot attention module on top that we run for a few iterations. And then we decode each slot individually using a CNN decoder and recombine the decoded images into a single image by letting each decoder also predict like an alpha mask. And this alpha mask is then used to recombine the predicted images into a single image. And this kind of recipe, like autoencoding for object discovery, has been around for some time. There have been quite a few works, specifically also like the Tagger model from Klaus Greff and others, Square, Monet, Iodine, Spare, Space. And it's a community that has seen quite some growth in the last few years. And if you want to learn more about this overall field, I heavily recommend this review article by Klaus Greff and others from ITSIA now at Google Research on this topic that explains a lot of the like high-level ideas behind this class of models. Now, what we can see is essentially that this simple autoencoder architecture can like route individual object components into particular slots and then decode each slot individually into an object, which is something that these earlier models that I've mentioned in the past slide also could do, but here we can do it in kind of a much more efficient way because we only need this very lightweight attention component to do the routing for us. So you can see we can decompose scenes of various simplistic environments into these slots here. And we also find that if you run this model for like, say, 3 iterations at training time, we can also run the model with more iterations at test time, something like up to 7 iterations at test time of this clustering algorithm. And the model keeps on improving, which is something that is quite nice to see, because it means it has kind of learned like a generalizable clustering algorithm that can actually benefit from having more computation, especially for scenes with like many objects. We see a lot of improvement later by having more outing iterations. And what we also see is that we can train the model on scenes with 6 objects, and then it learns to generalize to like scenes with up to 10 objects. This is something that we tested. So it doesn't need to have the exact number of slots that we use in the model specified at training time, but we can actually change this flexibly, both during training and also later at test time, and have the model generalized to more objects. And there, essentially in the model, there are two points where segmentation emerges. One is in the encoder attention, which the attention mechanism you can visualize, like we did the reconstruction in the past slide. And you can see that in the first iteration of this attention mechanism, the attention sometimes is still distributed over multiple objects. So it encodes kind of a mixture of both objects, but then it rapidly kind of specializes to individual objects in the scene. And similarly, for reconstruction masks in the decoder, we see a similar effect, only that if the encoder kind of encoded or attended to a mixture of 2 objects, then the decoder will kind of decode a mixture of that object, like it will decode an object in the middle between the 2 objects and kind of a hybrid of the features, like in this blue cube and the yellow cylinder, because they kind of mix the blue cube and the yellow cylinder, get decoded as kind of a green cube cylinder hybrid in the middle between the 2, which is kind of interesting. And so the model sometimes also, like what we've seen in the past slides, is that the model treats the background in kind of a symmetric fashion. It just distributes them across the slots. In some random seeds, it also figures out to like assign a separate slot for the background. And this is something you see here. And this is just one example of what happens if you train a model on objects of scenes with up to 6 objects, and a test time give it much more crowded scenes of up to 10 objects. And essentially what we find here is that the model still can kind of accurately decompose these scenes into slots. And then these individual slot representations can also be used for other downstream tasks if you want to reason about the kind of objects in the image. Another application of this model I want to quickly touch upon is set prediction. So you don't have to train this model in an autoencoder setup, but you can also use it in a kind of partially supervised setup, where now you would take the same backbone, you have slot attention on top, but now we would transform each learned slot representations using an MLP, like an MLP independently applied in each slot to get like a final output representation that is slightly more adapted to the downstream task. And then in this case, we have a ground truth set of labels that is in some arbitrary order, like Y1 to Y4 here. This could be descriptions about shape, color, or center of mass location of an object. And then we have a matching function like Hungarian matching to match the ground truth labels of the ground truth set to the predicted set in the model. And this is quite similar to some early works in this area, like deep set prediction networks, or also concurrent work that came out in the computer vision area called detection transformers, which exactly use the same idea, and that are now very popular for things like object detection in real scenes. So this seems to be like a universal kind of paradigm for training that is now that kind of got independently discovered in 2 different areas, and seems to be quite promising for future progress. And so the set prediction architecture then still allows us to visualize what the model learned by essentially visualizing these attention maps. And here in this case, we visualize the encoder attention maps after training the model in a supervised way on things like object properties, but also their bounding boxes. So the model gets a bit of information about the location of the objects, but it doesn't get the segmentation masks. And the model still learns to associate, it learns to extract the information from the right location in the image. Now these here are at lower resolution because we perform some downsampling before applying the decoder to make this a bit more efficient. And compared to this earlier baseline that I mentioned, this is using a similar permutation invariant scheme to predict a set, but it uses an internal gradient descent loop, which is much more expensive to run, and also seems to be a bit more unstable compared to our model. And what I'm showing here is essentially how the set representations get refined over multiple iterations. So this is what you see here is the very first iteration when the model just a random guess. But then if I now press forward, you see how the representations get refined over time. And after 4 or so iterations, the model essentially focuses on the correct objects and learns to learn good abstractions of those. And the interesting thing is here, at test time, you don't need to have this kind of matching and the set labels. So at test time, this model really just runs its backbone. It gives you these decompositions of scenes, and you get a predicted set of properties. I just want to quickly mention some work that I got excited about. The reason it came out, it builds on slot attention. So the first one I want to mention is object discovery from optical flow, where instead of using like actual scene images like the one we used here from very simplistic scenes. So one thing I should mention is that this type of model using autoencoders for object discovery, these type of models so far have struggled being applicable to real world scenes of complex textures, because the model typically then has a hard time discovering what the actual interesting objects are, like the high-level semantics features versus because all the complexities in the textures. And so very often these models then just cluster textures, but they fail at representing the objects. But recent work has shown that you can remedy this by essentially using optical flow as a representation for which you do the clustering in. Because optical flow doesn't have complicated textures, it essentially just the velocity of every pixel in the field of view, and then you can, so you need video data for this, but then you can have like these optical flow images and use exactly the same slot attention pipeline, and you can kind of discover real world objects or segment out like camouflaged animals in like complicated video scenes. So this is kind of an exciting direction to look further into, I think. And the other is this paper on Right for the Right Concept, revising neurosymbolic concepts by interacting with the explanations. This allows you to essentially take this kind of set prediction setup, have like a reasoning module or an explainer module on top, and have some kind of symbolic annotations that you can use to interact with the model to refine its predictions given certain instructions you have. Like, for example, you wouldn't want the model to focus on like the color of an object when making a classification decision. And because the representations of this model are so interpretable, you can very easily kind of build a model that can interact with these representations and use kind of symbolic annotations on top of it to refine it, which I think is also quite exciting. I just very briefly want to mention how one can apply the same kind of idea for learning about episode or like temporal objects in sequential data, which is a model or a method called ComplLE that I did during my DeepMind internship 2 years ago. And the idea here is to have a model that does competitive sequence attention to attend to event boundaries in like sequential data. And then we transform this attention into segmentation masks by using cumulative sums. And so this can be used in like robotics environments where you have like a robot agent doing multiple tasks, or like here in the simple grid world environment where an agent has to kind of visit or collect multiple objects, and you following some kind of hidden task list, and you would like to understand like the tasks, the underlying tasks that the agent has seen. And the overall framework is very similar to the slot attention framework. So you start by processing the low-level features, you have an attention mechanism, and then you can transform this attention mechanism into a soft segmentation mask. And with this soft segmentation mask, you can read out slot representations. And now, because we have sequential data, you need to kind of process with what you've explained so far, mask it out, and then process the rest of the sequence. So you can kind of apply this in online fashion on longer sequences. So you would read out multiple slots in that way. You predict attention masks, and then you can read out whatever you found to be one kind of temporal object in your sequence. And just to dive a bit into like how the attention mechanism works. So you have an attention mechanism, just a softmax attention attends to boundaries without any specific supervision. And you can transform this boundary indicator, this attention mask, into soft segmentation masks by essentially doing cumulative sums over the attention distribution. And in this way, you get like exclusive attention, exclusive segmentations that are always without any gaps in the sequence. And that way you can kind of have the model explain like every single time step in the sequence, but cluster it into abstract representations. And we can train this in multiple ways. Like we can train this in a set prediction setup, like with slot attention, but I think the interesting setup is training this in an autoencoder fashion, where then you just decode each slot representation again using, say, an RNN decoder, and using a mask loss with the segmentation mask that you get from the encoder to only get a loss for the part that it thinks it should explain. And I'm not going to, for the interest of time, I'm not going to go into results here, but basically what this model can do, at least in these kind of simple robotics and grid world environments where we tested this, is to find like the underlying segmentation of the task list of an agent just by observing its behavior, and also learning a like imitation policy that only imitates the individual parts of the task. So then you can recompose these learned sub-policies and perform new tasks on new task lists at test time, for example. All right, so in the interest of time, I'm gonna jump to the last part of my talk, which is about how to essentially combine both these relational inductive biases from graph neural networks and entity discovery into kind of an end-to-end framework that you can use to like reason, temporally reason, or like ask questions about like natural inputs using both kind of reasoning architectures and entity discovery models in a framework that some people call structured world models. And the overall framework here is essentially still following this kind of slot-based representation that I also mentioned, slot attention. And there have been quite a few architectures that take these one step further and have like a reasoning component on top of the low-level processing and abstraction part, but then also have like a reasoning or temporal prediction component on top that kind of reason about their relations. Things like graph VQA was one of the first papers on that, or relational neural expectation maximization, also recurrent independent mechanisms, and a more recent work on contrastive learning of structural world models that we worked on. And so the idea here is to essentially train this whole model end to end, but then make use of both abstraction and reasoning to be able to solve temporal tasks, for example. And the framework I want to focus on here is, again, around self-supervised object discovery. But now on top of that, we would also like to learn a action conditioned model of the environment in this kind of learned abstract latent space, where now every abstract variable in this latent space should ideally correspond to one object or one kind of component of the individual scene. And these should remain consistent over time. Like if you have the first component or the first slot bind to one particular object in the scene, it should then over time always correspond to this object and learn its dynamics and also its interactions with other objects in the scene. And because autoencoding, as I mentioned, is tricky to get working on kind of scenes that have complex textures, one of the innovations here is using a contrastive loss that essentially allows you to train this model without ever having to decode and without ever having to worry about complex textures in the input. And so this paper was something we worked on before, slot attention. So the encoder here is fairly simplistic. We have a simple CNN backbone again, but then instead of having like an attention-based grouping component, what we do is we take the feature maps of the CNN and we, let's say we have 5 feature maps, one for each object, and we flatten each feature map and pass it through an MLP. So basically we just say, okay, each feature map is one object. That's of course a very bad assumption typically, because that means as soon as an object changes appearance, it swaps slots. But and we have to have as many feature maps as there are possible, like object appearances in the input. So it's the same assumption that caption networks make, but it's still a fairly usable technique. And of course, one could replace it with slot attention to have a more flexible architecture. And the transition model in this case, also a simple graph neural network here of a kind of the message passing flavor, where we have an edge update function. We concatenate 2 neighboring features in this learned latent space to and pass it through like an edge update function, like an MLP, to get an updated representation of the relations between objects. And then we predict the future time step representation using the representation of a current object, the messages that are incoming, and also the action that a user might take or an agent might take in the environment. And we predict this with a residual connection just to be a bit more robust in terms of physics prediction. And the output of this model is then the updated representation for each object in the latent space. So the way we then train this model is using a contrastive loss directly in the latent space. So, and this is the main idea here, as I mentioned before, is that we don't have to do any decoding, which so far has been proven tricky for kind of scenes with like complex real-world textures and with these kind of structured latent space models. And on top of this, it also allows us to ignore task irrelevant details. For example, if you want to like build an agent that uses these representations, the agent might not want to care about colors of objects or complicated textures. It might only want to care about the identity of an object. And of course, it's dependent on the task, so one might never know this in advance. But with contrastive losses, the model learns exactly those things that are relevant for the particular kind of future prediction task. And the way we train the model is by having just a simple contrastive loss where we have a positive energy term and a negative energy term. So this is essentially an energy-based loss function. And instead of the particular choice we make here, we can also use pretty much any other energy-based loss function. The choice we use here is we have the energy of like a triple. We have essentially entity relation next entity, which we call here state action next state. So it kind of connects these kind of knowledge graph triples with like state representations in reinforcement learning. And also the loss or the energy we use here is essentially the same as what one would use in like knowledge graph embeddings, like translation embeddings. So we have a distance function applied on the latent representation of one node, plus a transition model, which is an additive model that takes into account the relation between those two and the representation of the next state. And so we compare those. And so the relation is given by the kind of jointly by the current state and the action that tells you how like the two states are going to be related to each other. And this energy function for the positive states, we then couple with an energy for the negative states to make sure that the representations don't collapse, because if we don't have like a negative energy term, like having just a constant value for all the representations would be a valid solution. So we need some kind of negative energy term to counterbalance this. And so here what we do is essentially just compare the learned state representation with a learned representation of a random observation, like a random state from the environment. And we make sure these are pushed apart. And so this learning algorithm suffices, or this kind of learning loss suffices to learn object representations in at least the simple environments that we tested for. And so the environments here are some synthetic environments that we build for moving around objects in like very simple grid worlds, where you have an agent that can perform actions like choose an object and move it to the right or move it to the left. And also games like Atari, where you have like actions that control the pedal, or the spaceship in Space Invaders, but also environments where you don't have any actions, like you just observe gravitational physics simulations. We have three bodies swirling around each other, and you would like to understand the individual components of the scene and also be able to model the physical relationships between them. And so the difference between these environments are mostly in the types of actions that we have. We either have actions for each individual objects in these simple scenes. We have kind of global actions in Atari, where an action can affect everything in the scene, or we have no actions in these physical simulations. And I'm just showcasing some simple results here. So what we essentially find is that despite not being trained with autoencoding, which is what people have done before for like object discovery type architectures, is that the model still seems to learn some specific feature maps for the particular objects in the scene. So these are not attention maps now, these are actually really the plotted weight values of the feature maps of the CNN. So it's kind of a funny way of visualizing what the model learns, because it could also be the inverse of that, what we see here, which would be equally valid. But essentially, the ones I picked here, they kind of show nicely that the model is able to decompose the scene into like the relevant parts in order to be able to solve the task. And what I think is even more interesting is that the model learns kind of an interpretable latent space. And what I'm showing here is the latent representation. In this case, we actually really just choose a two-dimensional latent space for each object. So this is not a projection. This is actually like the latent space that like directly visualized. But we also found that if you choose a higher dimensional latent space and then do PCA, you roughly get the same. And here in this particular case, the model is trained with all objects being movable. But then at test time, we freeze the red, blue, and purple and green objects in some random positions. And we only let the agent move the yellow object. And so what you see is that it keeps the spots empty where the other objects are. So here we visualize essentially the latent space of the yellow object slot. And the edges are the transition that the model learns. If we now apply like actions in the environment, then the model kind of learns to move its representation exactly on this grid, but it avoids the spots where the other objects are, which are also represented in Lincoln space. And it can only do this because it has like this graph neural network that informs it about where other objects are, and it can kind of predict the effect of an action given that there's now a different object in this particular spot that it also learned in its later representation. And so I think this is kind of a promising sign that these types of models, they actually they work, they can do something interpretable. But of course, there's still a lot to be done in order to make this kind of scale to the real world complicated data, going beyond this kind of grid world assumption, and making this work on like more relevant tasks like for robotics. So to summarize, I essentially talked today about relation discovery as one interesting aspect of relational structure, where we essentially find that the graph neural network inductive bias, or the inductive bias, this relational inductive bias from its models, is not only useful for learning with graph structured data, like classically graph neural networks have always been applied to. If we're given some kind of graph and we want to learn like representations of nodes, or maybe also of the graph, or maybe also of edges in this kind of graph data set. But we can also use the same kind of architecture for a learning in data sets where we're not given any kind of graph, but we kind of either assume kind of a fully connected graph, or we let the model figure out the relations by itself by using some kind of attention mechanisms or sparsity mechanisms. And what I'm most excited about recently is this part on entity or object discovery, where we would like to find symbol-like or composable abstractions in an automated manner that are dependent on the task. Like for one particular task or context, the model should be able to find the right abstraction. And it should do this without ever being explicitly supervised, because we cannot possibly supervise a model for all the possible contextual abstractions that one can build. So this is something that needs to emerge from just the way the model is trained. And I think this is a major open challenge in machine learning. And hopefully this will get us to more kind of interpretable and more human-like kind of machine learning reasoning models. And I think that differentiable attention mechanisms as kind of an interface for mapping between these high-level abstract symbol-like representations and like low-level visual features are a promising direction. They might not be the only one, but it's definitely something that we've seen evidence for to be working even on now more and more complicated kind of visual scenes. So what's next is basically, in my opinion, to do like structure discovery on other domains like text to speech or video data, where you go beyond like simple images, simple scenes, but use kind of the rich information that we have in like in the wild videos to really learn like useful abstractions that are interpretable, but also to explore other learning paradigms. Like I've mostly talked about autoencoding and contrastive learning, but one can also, of course, train this with jointly with like an agent for things like reinforcement learning targets and so forth. And I think there's still a lot to be explored. And lastly, I think combining like structure discovery and reasoning and prediction is still kind of a major open challenge. And ultimately, I think we want to be able to learn the optimal graph structure, both in terms of entities and relations for a downstream task, just given like the context of the problem, and not have to supervise both the entities and the relations in the whole process. And lastly, at the moment, I think we're a bit short on benchmarks, and benchmarks are really crucial for measuring progress, both in terms of benchmark data sets and also in terms of metrics. I think there's still a lot to be done to really highlight what the open problems are, and to also measure progress on challenging but still reachable tasks. So just as a last word of like advertisement, it's already almost a year ago that I graduated from my PhD, but if you're interested about these things, what I described in my talk, a lot of the topics here are covered in my thesis, like both on learning with explicit structure, like node classification, link prediction, but also on learning with implicit structure, like relational inference or entity discovery. So if you want to learn more about this, and if you're interested, you can find the thesis by just Googling for the title. Or I also have like, I think, a handful of copies left. So if someone's interested, I can also send out hard copies. All right, so that's it. And I would like to thank all my collaborators, both for slot attention and Google Research and ComplLE at DeepMind, but also earlier collaborators at the University of Amsterdam, Toronto, and also the Free University of Amsterdam. And I think we have around about 5 minutes for questions left, so I'll end it here.
Thank you, Thomas, for this great talk. I see already Stephen definitely has a question. I also have questions. Before giving Stephen the opportunity to ask, let me remind all the people that follow us online on YouTube that if you want to ask a question, please make use of the chat option, and then we can ask here, so to say, live for you. Stephen, go ahead.
Yes, so Thomas, I found your description of GNNs and relational discovery really interesting. Just something I wanted to say is recent advances in inductive logic programming, and particularly meta-interpretive learning, have demonstrated that algorithms can be rediscovered from examples with understandable automated problem decomposition. I was wondering whether GNNs can learn or discover algorithms, for instance, like quicksort.
I think that's a great question, and there indeed has been some work in this space, especially from Petr Veličković at DeepMind, who made like algorithmic reasoning with graph neural networks his prime research agenda and focus in the last 2 or so years. So I can recommend looking into his more recent work. In many cases, like the focus of these methods is still to kind of imitate algorithms using graph neural networks, and then seeing that, okay, just given an algorithm, we can learn to imitate it pretty accurately. But that means the model has the capacity to essentially model algorithms. And I think being able to discover algorithms is just an additional step that might need just the right kind of learning paradigm on top of the architecture, or the right regularization. And I think these also can be combined with like insights from inductive logic programming to get like these models to focus on the right things, to learn the right abstractions.
Any other questions? So I have one, which is maybe a little bit more into technical details. So because of the softmax, and you said, oh, it's so nice because the slots are competing for the attention or for the explanation. Now, if I think of visual reasoning, isn't there also this question of what if one object is in front of the other object? And shouldn't we somehow tightly integrate reasoning with the slot attention or the competition for attention? Because so that's what we currently wonder about, whether there's a way to actually put some real visual reasoning in there, and not only after we sorted out the attention slots.
I absolutely agree, and I think that's a really great question. And so my view on this is that the slot attention component is only really there for like gathering and structuring like new visual evidence. But if you want to like say apply something like this in a video, what you want to do is like have another kind of reasoning component on top that maintains, like if an object is occluded, maintains its representation, lets the model know that it's there, and then kind of can query the input and kind of check if it's visually there. But then if it's not there, it still kind of can update the representation based on like the new representations it gets. And like I think still doing a softmax over the input or over the slots to gather like new visual evidence, I think makes a lot of sense if you have, in addition to that, some kind of reasoning component on top. Because
so you believe it's the reasoning component, and we should not try to do something like the anchors or whatever we know from YOLO to put that in?
I think a lot of these things can be resolved by just consistent temporal modeling. If you like want to like, if you have occlusion over time and you want to consistently maintain object identity, then I think just having temporal modeling on top should be sufficient. If you want to model full occlusion on a single scene, like infer hidden components that are really not inferable just from a pure observation, then you might need something else.
Makes sense. Okay. Yeah. Any other questions? Volker, Paolo?
Yeah, I can ask a question.
Luke, you can also ask. You're online, right? So Luc, you have a question. I can repeat it. What would it take to learn how to plan? But you may also just ask him himself.
Okay, so I'm wondering, like, it's a lot about dynamics and about recognizing objects, but what if the goal is really to reach particular configurations? So you have like goals and kind of implicit actions. How do you see these techniques ultimately will apply to that kind of challenge?
That's a really great question. And I think ultimately, like we can use any kind of end-to-end kind of planning technique that also works in abstract spaces, but then just connect them to visual input. And so if I think, I mean, reinforcement learning type learning could be used to learn like the important transitions, so that we can then learn like more like geared towards the task kind of model. But you could also use imitation learning if you have like rollouts of an agent, and also maybe conditioned on some kind of goal, to be able to then use the learned model to actually do something like some kind of planning, like model predictive control or something like that, where you maybe plan 1 or 2 steps ahead and then check if like the new visual input matches your expectations and then replan based on that. But I think ultimately the way you train these models can be done like with any other kind of technique used for model-based learning or model-based RL, where you would like to plan. I think a more interesting question on top of that, which is maybe implied by what you said, is like, how can we also learn temporal abstractions for like really kind of making long-term jumps in terms of planning? Like, I don't know, if you want to travel to a different country, you might not want to like learn about the individual kind of time steps at like a fixed time horizon, but you kind of want to jump ahead. And like learning these temporal abstractions, I think that's still kind of an open question on how to really integrate that.
Thanks.
Any further questions? Okay, so thank you, Thomas, for joining us today. I still have tons of questions, but I think we can also take them offline. So yeah, it was wonderful. Thanks a lot.